All right, there it is. All right. Hello, everybody. We'll get started here. So this is AI-driven analysis of police body-worn camera footage, practical applications for police. First, we'll go through introductions, go over the ideas behind the project, how we've gone so far, some challenges, future work, and then we'll take questions at the end. To start, my name is Adrian Martin. I've been a data analyst and crime analyst for the Rochester Police Department in New York State for 17 years. Right now, I'm in the Office of Business Intelligence, where I've been for 9 years.
Hello, everyone. My name is Annual ASEBP. I'm a BSMS Computer Science and Mathematics student at the Rochester Institute of Technology, currently working as an ML researcher on the OpenBWC project. Hello, everybody. My name is Anita Serbinovska. I'm a computer science and mathematics student at the RIT and a machine learning and NLP researcher on the OpenBWC project.
Hello, guys. I'm Vivek Sandil. I'm MS Artificial Intelligence student in RIT, and I'm currently an ML researcher in OpenBWC project.
My name is Ernest Fouquet. I'm a professor in the School of Mathematics and Statistics at the RIT. And I'm the one who caused trouble by wanting to make this analysis happen. The great man.
Yeah.
Thank you.
Yeah, and then additionally, Dr. John McCluskey was not able to be here at the conference, but he's also a big part of the project. He was at RIT when we started. He's since moved to SUNY Albany. So the idea behind the project is that, at the Rochester Police Department, we've had a body-worn camera program since 2016. And in total, between 2016 and 2023, when we started the project, we had about 14 years of continuous footage that nobody had watched. And it's, entirely impossible for somebody to watch that. But on top of watching it, if you wanted to code it, it would probably, take 4 to 5 times, it takes 4 or 5 times as long to code a video as it takes to watch it. So it's totally impossible to go through all the video, which means that we can't really do pattern detection. We're pretty good at RPD of drilling down into a specific incident. So for instance, when there's a use of force, it gets reviewed by the officer sergeant and also by internal affairs and also by training and also by command staff. But nobody reviews the 30 similar incidents that could have resulted in use of force but didn't. So we can't really find patterns. So with the use of force example, we can't really figure out what led to the use of force without looking at all the incidents that did not result in use of force. So this was our overall project plan when we started. We have about 155 terabytes of body-worn camera footage from 2016 to 2023. We're going to move it to RIT. They have a research computing division where they just have huge servers and super fast processors. We're going to basically do some exploratory data analysis, build algorithms, build some descriptive data sets that we can post online for the public and for other researchers. And then also the due diligence is kind of basically confirm that there are no unreported uses of force on video. Training assistance, stuff like looking at de-escalation. And the learn part, we just had a lot of questions about policing in general, especially since the footage spans 2020. So for instance, officers say, anecdotally that they get crowded on scene more frequently post-2020. With this footage, we could, confirm or reject that hypothesis. It turns out that we had so much footage that even the research computing division at RIT could not handle it all. So what we're doing is while they're getting up, spinning up the servers to be able to hold all of our stuff, these guys are building the pipeline with video that we've previously released through Freedom of Information laws. So they have about 850 videos, and they're using that to build the pipeline. And then once that pipeline is built, hopefully the capacity at RIT will be online, and then we'll start feeding all 155 terabytes through that process.
Now let's talk about our solution and how are we using technology to make the review process of the body-worn cameras recordings much faster, easier, and more useful for police training and improving safety practices for both our police officers and our community with a goal to support law enforcement agencies with open source, trustworthy, and secure AI tools. Now, throughout our whole project, we're only using open source tools instead of proprietary software because they're much more customizable and adaptable by our community. They're transparent. Our team is all about transparency. And of course, anyone, researchers just like us, other departments, law enforcement agencies can use this system, AI-based system, adapt it, work with it, and also test it with their own data. And our goal for police officers and supervisors is to help them, assist them with this AI-based system to find key important moments in these recordings. For example, we would like to find a subset of recordings or clips showing good de-escalation strategies or strategies where a police officer handles a situation very well and helps our community. And we would like to incorporate that and use that in our future training police sessions. So even though we are using open source tools, this is not going to replace our manual verification and our human judgment. This is going to help us and assist us in the information retrieval and finding patterns in the output. Now, I would like to motivate this even further and help you understand the question, well, how can this assist us and help us? How can this help us, officers and departments? But before that, I would like to start by saying that these are our four main ethical areas that we're going to base our AI system on. And also, anytime we're using AI, especially in sensitive areas like policing and handling sensitive data, we're trying to be very careful and thoughtful about building our research pipeline and our research process. So first, it's fairness in AI models. Our data set consists of diverse incidents, scenarios, police-citizen encounters to reduce that bias that comes with these AI-built models. Next is transparency, like I mentioned before, transparency in decision-making. So we don't simply want our open source AI-based system to feel like a black box and no one will know how the result was reached. Instead, we would like you to go back to the algorithms and refine them, tune the parameters to get the results based on your requirements. Next is data privacy and security. Of course, privacy and security while handling this sensitive data are top priority, and everything runs securely through our RIT's computing security lab. Everything runs locally through our machines. Nothing ever was stored on the cloud, nor was run on the internet. Everything is running offline. And of course, it's collaboration. We would like to continue working with our police officers and advisors because, as we all know, technology without context cannot solve real-world encounters. And all of this brings us to this diagram, or our research pipeline, or what we call the OpenBWC multi-perspective analysis. So when we say multi-perspective analysis, we simply mean that we're going to look at a single recording, a body-worn recording, from 3 different angles or perspectives. So we have the audio component, the text component, and the image component. So let's first start, if we can imagine, a single BWC video, which is securely stored in our database as an MP4 format. Now, the next step is to convert that video format into an audio file format, into an MP3 format, to pull out the sound from the recording. And what we perform next is what we call speaker derivation, or identifying who is speaking at what moment at a given time. Is it a police officer or is it a civilian? So once we have multiple audio file formats for all the speakers in our recording, we are going to convert that through our speech-to-text model. So we're converting those spoken words into a transcription, into a transcribed data set. So now we're in the text component, in which we're trying to find the meaning behind those interactions, the meaning behind those spoken words. Also, we're summarizing the key events in the recording and storing everything in a searchable database. So whenever you're trying to find a footage of your interest or a summary of event, you can simply search that in the database. And so right now, we're mainly focusing on the audio and the text component, since they're strongly correlated to each other. However, the plan and the goal for now for the image component is to detect object detection on different visual frames from the recording to detect different objects in different scenes relevant to the encounter. And you might be wondering why all of these 3 arrows are coming from these 3 different components. So since this is a multi-perspective model, they should all, even though they're all running separately as modalities, they should all agree on one single output with high score and high accuracy. So for example, if you have video recording and you listen to it manually and you hear a gunshot or maybe someone mentioning a gun in the recording, then that will be transcribed in the textual component. Now we are here in this modality, but it will also be detected through our object detection model in the video frame.
Yeah, so let's first start with the data. We have around 840 RPD videos that was taken from the Rochester Police Department, which was obtained through Freedom of Information Law. Each of these videos are approximately of length from 10 minutes to around 3 to 4 minutes. So it is so hectic job for a single investigator to go through and swift through all the videos and to understand what is exactly going on and if there is any gun involved or if there is any violence involved. So what our initial first step is, whenever an investigator comes and asks, give me a traffic stop footage where gun is involved, we would like to do it within the coffee gets cold. So we propose a modular approach where one of the module is speaker diarization and transcription using Whisper AI and using open source large language models for summarization, and at the end we use Postgres for full text search and vector based search. Now let's look into each of these steps one by one. And so as a pre-processing step, we first convert the MP4 files into audio MP3 files, and we split it into smaller chunks. Now, why do we need to do that exactly? It is mainly because of the constraints, computational constraint that we have in our computational, RIT's computational clouds, systems. So we initially tried to process a full video without chunking it, which was around 10 minutes. And the speaker source separation part required a whopping 128 to 130 GB of GPU, which is so huge and which is so costly as well. And it is definitely not a scalable approach, given that we have a lot of videos and given that the videos ranges from even 3 to 4 hours long. So we had to chunk it down, and we experimented with different chunking sizes, different window sizes, and we narrowed it down to 30 seconds, which worked optimally with our computational resources and the time taken to process each videos. So we use A100 chips, NVIDIA's A100 chips, which is 40 GB version. And we also tried using noise cancellation, but we ended up realizing that it is not a very good approach because we started observing a degradation in the transcription accuracy. That is mainly because these noise cancellation works pretty well and it works for human observations, but the thing is, instead of just removing or cancelling the noises in the background, it also tends to reduce the volumes of or amplifications of the normal speakers. So the police officers are usually louder because the body-worn camera is on the police, but the civilians' audio, because they are usually far away, is very low, and this noise cancellation reduces it even further. So eventually we had to remove it. So then we'll move on to the speaker source separation or speaker diarization. What is it exactly? It is basically when audio has n number of speakers, we try to separate it into n different audios, with each audios having only these one speaker's waveforms. So when we input a speaker audio with 2 speakers, this module gives out 2 different audios, with each of the audios containing only the audios of one speaker. And why do we need this exactly? Is because in the transcription accuracy, the state-of-the-art transcription modules that we have, like Whisper AI models, they are trained on studio dataset, like Zoom call meetings or the studio dataset, which are practically trained or created for this training purpose. So those kind of data are very crisp, very clear, a single personnel speaking, and they have very less noise. and this data is not noise free. RPD data is full of noise. So we wanted to bring this audio as close as possible to the studio data set, and one of that step is to do source separation, where we split it into single speakers and we pass this down the lane. So let us get into the nitty-gritty of how this speaker source separation works. We use an algorithm called SEP reformer, which is a asymmetric encoder decoder module. What basically happens is this chunks that we did in the previous section is passed down to the audio encoder section, where this audio waveforms is converted into a latent space. Latent space in a layman term is basically converting it into a more robust representation that is easy for the computational tasks. And this latent representation is passed down to the source separation module, where it uses different kind of masks to eliminate individual speakers. And these masks are then inverted to isolate those speakers alone. And these latent space of individual speakers are passed down to the audio decoder, where this latent space information is then converted back to the original format, which is MP3. But in this stage, instead of giving out one audio, it gives out two different audios in our cases, because there is two different speakers. And these two different speakers, or audios of two different speakers, are passed down to the transcription module. And I call upon Angela to explain more about transcription.
So now once we have separated the speakers, the next logical step for us is to understand what was actually said. So we take these separated audio files and we pass them to Whisper AI, which is a state-of-the-art AI speech recognition, another open source model that turns speech into text. And after the transcription process, we take random subset of these transcripts and we manually verify for ourselves how well did this model perform. In most of the cases, it did a very well job in the transcription process. However, as mentioned before, in some noisy environments or when we have overlapping speech, probably many people in one scene, the model struggles a little bit by confusing the speakers or repeating some words. So on this slide, I have an example of our transcription process or speaker identification. And so this is two sets of random transcripts taken from the same audio file. On the left, we have the officer transcript, and on the right, we have the civilian transcript. So everything that we've seen that is highlighted in green color, that means that the model, Whisper AI, gave us 100% correct accuracy. However, everything that is highlighted in yellow color, that means that it is a partially correct transcription. But as I mentioned before, we have some repetitive words here. However, that is due to the fact that for this current stage of the pipeline, we are using Whisper AI base model, and Whisper AI has multiple models. However, this is something that we're working on, and in the future, we are planning to use a more advanced Whisper AI model that will give us even higher accuracy. After the transcription process, we take these two sets of transcripts from both speakers and we merge them back together to get one single transcript alongside with a predefined prompt, and we feed them into large language models or LLMs. So what do these models actually do? Well, they read the whole transcript and then they generate a clear and intelligible summary of the main events of the BWC footage. So they will tell us things such as how did the officer behave, how did the civilian reacted, how was their interaction, was there any use of force, tension, or violence detected in this footage. And so these kind of summaries will help officers, supervisors, and us researchers to better understand what actually happened without having to go back and watch hours of footage. In the next slides, I have examples of different LLMs. We experimented with different LLMs in this current stage of the pipeline, and we will see how LLMs such as Llama 3.3 and Gemma 3 generated this kind of summaries for the same transcript file. Okay, so let's start off with Llama 3.3. This model's output was very clear, organized, and structured. It clearly separated the two speakers. Well, in this case, we just have the officer and the civilian, and it generated a brief summary of the main events for this specific BWC footage. At the end of the file, we can see this section, a text identified that this model generated that states that in this specific example, there was use of force, violence, and escalation detected. Now moving on to the next model, which is Gemma 3. This is for the same transcript file. And this model's output was less refined and structured. It feels a little bit repetitive in the first part of the summary because it combined the two transcripts of both speakers instead of summarizing what actually happened. However, at the end, we can again see this text section generated by this model that is very similar to the one produced by Llama 3.3, which will be helpful for later and further analysis and interpretation in further stages. And the last step of our pipeline is designing the database for effective search. So we designed this database using PostgreSQL, which is fast, searchable, and scalable given the nature of our data. So this database stores all of the summaries that I just talked about. And the goal for this database is, again, that officers, supervisors, and us researchers can retrieve any relevant information for further analysis, going back to a specific BWC footage, such as was there use of force, escalation or de-escalation detected in a specific BWC footage.
Yeah. So, of course, everyone here agrees that processing body cam footages is hard. So, I'm here to talk about the challenges that we faced in processing this video. Firstly is the dataset. Of course, the body cam footage dataset is nowhere clear to clean. It is noisy. It has traffic noises. It has people yelling at each other, and it has the radio interference. And it is not a single category of videos because it has nighttime videos, it has daytime videos, it has indoor videos, it has outdoor videos. And it is also not a single style of conversation going on because we have traffic stops and we have gun violence involved. So we have all ranges of videos. So this is the classic example of how a data set should not be, how a researcher should not select a data set. So that is the main challenge for us. And the next challenge is the GPU constraint. So even though RIT has a very good infrastructure of GPUs, the researchers are provided with state-of-the-art NVIDIA GPUs, A100 chips. These modules that we use are also state-of-the-art, and they are GPU demanding. They are so hungry for GPUs, and each of the modules that you saw that we explained about are carefully selected to fit in our infrastructure and for our data set. So these modules these pipelines are carefully designed that each of the modules can be replaced because each of the modules has state-of-the-art challenges which are being solved as we speak. Even the large language models that we used, we had to experiment, reiterate that step a lot of time because we saw a rapid, drastic improvement in open source modules that are being released. Even as we speak, there were a lot of modules that are being released day by day. And the ambiguity in speech patterns is also a critical issue because universal source separation is still an unsolved issue. What I mean by that is when we are unaware of how many speakers are involved beforehand, it is hard to split them. So in our approach, we need to know that how many speakers are there in that particular audio, which is not usually the case. So for this research, we stick with a module which was trained to separate two different speakers, which would not give accurate results when there are more than two speakers. So this is an problem that we tend to resolve in the future research.
Well, so what's next for us researchers for the OpenBWC team? Well, from technical standpoint, we will try on expanding the multi-perspective analysis or the model, the diagram that we showed earlier, to integrate multiple different algorithms on the different components. So first, we'll start with voice stress detection to assess the emotional cues and the tone of each of the speakers in the recording. Next would be sentiment analysis on the text component or modality to evaluate tone and intent to detect the sentiment of the sentences, whether it's being positive, negative, or neutral. And like I alluded before, object detection will go on the image component or modality to identify visual elements in the footage or what is happening on visually, who is holding what is happening in the surrounding. But of course, we will not stop at only looking at only one video at a time. We will try to link patterns across multiple recordings and incidents and encounters, because of course in our data set we have multiple recordings from the same police-civilian encounter, so we will try to cluster them and classify the similar events. But of course, most importantly for us is collaboration with police officers, departments, not just from Rochester, but across our nation as well. So we can all analyze these police-civilian encounters and real-world problems together to refine our open-source AI-based system, because as we believe that your experience is what really matters here, what makes this project meaningful and these recordings valuable. Thank you.
So I think one question a lot of people are going to have is, how can my agency get started with this? And I think there are three big areas that an agency needs to already have, needs to have in place. Number one, you need to already have a lot of your own body-worn camera footage. So with RPD, we've had a pretty successful program for 9 years. We've audited our officers to make sure that they're turning their cameras on when they're supposed to, and it's well over 98%. So we know that the data set we're working with is representative of the actual encounters that they're having. You have to own your own data rather than just be licensing everything and have a third company store it and own it. And it really helps to have a pre-existing partnership with a research university. Myself and Dr. Fukwe had already worked on and completed a prior grant prior to this with RPD's, where we looked at RPD's uses of force and did natural language processing on the narratives for those. And so that kind of, that builds trust. So when we tell the chief we're going to hand over all of our body-worn camera footage videos to somebody, it's like, oh, well, it's the guy that already has all of our uses of force. So that's all right, And then the university, it's, obviously important that they have a strong technical, math, computer science, et cetera, program, but also the criminal justice, the sociology type, the program is also really important. Dr. McCluskey has been super valuable in making sure that, we are not like trying to repeat other stuff that other people have done and not running down a rabbit hole. And then the infrastructure is really important as well. So RIT's research computing program, like the guy said, that they just have, so many GPUs available for us to use. And even with their amount, it's still kind of tight. We still have to design stuff within the constraints. And it would be much, much harder if we were relying on cloud computing, and much more expensive as well, where we were sending data to the cloud and getting it back, sending it back, and spinning up virtual machines all the time, et cetera. So those are the kind of the three areas that you need to get down if you want to start to replicate this project. This is a QR code. We have a paper up on Archive. If people want to check that out, I'll leave it up.
I just want to add one last thing here for all of you guys listening here. The concept of this collaboration, in a sense, I'm a preacher, so my voice is big for this. This microphone is too much for me. This is such a great opportunity for me to just. I just want to say to everyone who's listening here, police officers, citizens, that when Sir Adrian and Nick called me from the RPD to tell me to be involved in the project, starting from the NLP before that, and sponsoring many of my conferences out in Rochester, I wanted to do this because I don't say this to impress you. I love police officers. You are precious to me. All of you in this room who are police officers, you're precious to me. I know that there's a wrong perception of some police officers in the community, and I'm hoping that the research that I'm spearheading will help correct some of that. Now, it may just be a tiny little epsilon in the vast universe of perception, but I would love to see the science put the data. I heard evidence-based. This society is so wonderful.
evidence-based. We want to put evidence-based to help our community and help all the police academy show that our police officers could do their work and the community can have that wonderful relationship. But I don't want to finish without asking you guys to give a big round of applause to this man. He's always hiding. Really, he's an amazing, amazing collaborator. Adrian, because of you, I want to do this. I'm telling you the truth, because when I work with you and when this one came up and I said, I want to keep working with you. And that idea of collaboration that my kids repeated many times is awesome. Thank you for being you. I appreciate you. Please give a big round of applause to Adrian Martin. And last but not least, if you're not impressed by my children, you are wrong. These guys are smart kids. They do a lot of stuff. I'm just behind the scenes. I'm just saying, hey, let's do this. Oh, this is a grand plan. And the next day, Anita will come to me with a great idea. Angela will come to me with a fabulous idea. And what about Vivek? He'll come up with brilliant ideas. So we need this kind of stuff. I just wanted you to recognize this, all this wonderful team we have with a big round of applause. Thank you. Thank you. Thank you very much. Any questions?
Any questions?
Yeah.
Adrian, as you guys build this out, is there any thought as far as the process goes to building in maybe some intelligence aspect into this or investigative component that you can identify certain things as you start to take a look at those stuff?
Yeah. So the question is whether we are thinking about building in intel or investigative tools with the project. So one thing that always comes up is facial recognition. And when we accepted the money, City Council, Rochester City Council expressly said that there will be no facial recognition with this project. So we're doing facial recognition in the sense that we recognize a face, but we are not saying that this face is like that face. We're not, doing anything more than saying this is a face. So we're not doing any facial rec. We are not. I mean, I think probably it would be a few years down the road that we would try to do anything with investigatory helps other than just the summaries, because there's always when an attempt ID goes out and a cop recognizes it and, oh yeah, I dealt with that guy, but I don't remember when or where. But if we had a summary of, that cop's interactions that they can just filter, then that would help bring up, all right, that's the CR number. Now I'll pull up, okay, that's the field intel card I filled out. All right, yeah, that's the guy. So I think that would be a real help, but we're not going to be tailoring it towards investigation stuff, anything more than that. Yep.
Is there like an interval period that you guys are able to apply? As you're doing the multimodal analysis, and you're doing object detection sort of in one strain, and you're doing sentiment analysis and these various other text processing analyses. How do you bring them together in time across the transcript? Are the various sentences being blocked into, you mentioned these 30-second intervals for processing purposes. Are those now also tags and can be corresponded to object detection, or what level of granularity are you able to achieve?
Yeah, so the question was, how are we integrating the image inference and the inference through transcription? So the answer is, we have currently worked on audio transcription part, and integrating that, the idea is basically to experiment with the sizes of the split, because that is how you time the transcription. See how much the chunk size is more effective, whether 30-second chunks gives more reasonable response, or whether 15-second chunks gives more reasonable response in terms of text and images. When I say 15 seconds, it should match with 15 seconds of video, and all the object detection inference that we gather in that 15 seconds, all the frames in that 15 seconds, it should be evaluated. Also, object detection, usually people think of detecting the object in that single frame, but that usually leads to a major flaw. You want that object to be in the frame for like 2-3 seconds for a set time to see if that really makes sense or is it something hallucination happening in the object detection. So these are the experiments that we would like to conduct and narrow it down to a certain split size, which gives you effective inference in both domains.
The alignment, right? I think your question is in terms of alignment.
Yeah.
And I think he's extremely aware of that.
Yeah.
So it's perfectly aligned. I think that was the nature of the question, right?
Yeah, absolutely.
It's aligned, yeah, the alignment is taken care of. But the alignment, like he's saying, is not guaranteed to be in the object detection. It's not like frame to frame, it's like, there's some intelligence to make sure that if this object appears, enough of your
Presence of it during that period.
Exactly.
Yes.
That's right, the presence of it during that period is what we care about, because that's what matters to you. Yeah. Thanks for that good question. That's a question that arises all the time.
Yeah,
Andrew, with the thousands of hours of unviewed footage that you guys are going over, what are you guys doing about, for the department specifically, about uncovering misconduct, policy violations, things like that, that may have not been seen if you didn't do this audit?
So we have an easy out for that, and because our bargaining agreement says, I think it's 18 months. You know, if the thing hasn't been caught in 18 months, then you can't face discipline. And our footage, because RPD transitioned to a new camera system in 2023, that was an easy cutoff to say, all right, this is our data set. So that means that anything we're looking at is outside that, that window for discipline. But, if we uncover something criminal, then we just tell, the chief, and then he decides what to do. So, yeah.
I think there is one more question.
Oh, that was the same question. Yeah. Let's see. Any other questions? Yeah, in the back.
Did you guys see any instances where it just completely got it wrong? Like, if you reviewed it, it was just not at all what the model was saying, or I don't want to say fabricating,
Yeah.
but maybe some white lies there.
Yeah.
Is there anything like that?
There are incidents of that, but it happens more often when there are a lot of quarrel going on, and when there is serious violation going on, you see 4-5 officers come in as a backup, and you see a lot of them shouting at each other to de-escalate the situation, and so you can't understand which officer is shouting, especially when the pitch is so high. When people are shouting, all the officers' voice seems to be the same. So, in those scenarios, that is when the speaker source separation module that we have, it is not, it is still an unsolved area of research. So those are the scenarios where I would not call it hallucinate, but it doesn't even have the clean source of truth to analyze that. Yeah.
Any other questions? Yeah.
Yes, in that respect, so if you have 4 different officers on scene, are you guys reviewing each of those officers' body camera footage and putting that all together for one large file?
Yeah, currently we are not classifying or grouping it based on all those data, based on what the scene is and what the data is. Currently we are processing all the body cam footages as a whole. We plan to classify it later on. And in the later stages, we plan to analyze multiple perspectives of the same footage to see how accurate the inspections from each footage or how collaborative the information from each of the scenes are. But for now, we are trying to create a pipeline that is able to infer from any kind of body cam footages that we have. Yeah. I think there was one more question.
Yep.
Yeah.
I had a question, this is probably farther in the future, because you're working on just the voice recognition right now. Eventually, we try to also incorporate positioning of the officers in the videos and where they are, if we're talking about use of the voices, right? Are 4 officers surrounding the guy, are they too close to him, are they talking from a position that disadvantage to? Does that make sense?
Yes. So what you're asking seems to be easy. It is like the distance mapping. In theory, it sounds like a simple problem to solve, but
I know it's very difficult.
yeah.
in the future,
Yeah.
is that where you would want to go?
Yeah.
Yeah.
Absolutely. In fact, I think that one of our meetings, somebody was asking that, like the concept of distance, is asking the position.
Yeah, yeah.
Yeah.
Pretty much the same question was asked when we presented to some of our collaborators in Rochester, but it's a very, like Vivek was saying, it's a very difficult problem. So it's a very, especially what Sir Adrian started saying, that some officers complain of crowding at the scene starting in 2020. So, but we have to run that hypothesis. Is it the case that they're really crowded? And the only way to run that hypothesis, to answer your question, are they crowded? Where are they standing? What's happening around them?
Yeah, because currently, where I'm from Los Angeles, we're doing it by hand, right?
Yeah.
We're saying, officer, mark on this map where you've been standing, when you're talking,
Yeah,
we're trying to match it to the.
Yeah.
It's
So-
very difficult.
Yeah, so the issue there is, as humans, we know the perspective. We know when we see, okay, average human height is this, and average officer height is this, and average height of the car is this, so that based on those perspectives, we measure stuff. But in terms of when you want a computer to know it, you want the computer to know the standard measurements, like what is the average car height and what is the average, some unit of measurement that should be in the frame. And usually it is not there. Like there is no standard object like a car or something like that.
A ruler.
Yeah, a ruler or something. So that is the key issue that would be facing. But yeah, that is in the horizon of
But
solving.
we love these questions, right? Because like we said, I said to somebody earlier, science fiction today is science fact tomorrow, right?
Yeah.
These questions, it gets this very brilliant student and myself thinking very hard on how to standardize so that we can actually answer that question. And the fact that the person is coming back to us over and over again means that maybe it's time for us to start really thinking hard about it. Right? Very interesting question.
Any other questions? All right, perfect.
Okay.
Thank you.
150.
Thank you.